Hey kids, can you come here for a second? I got a question for you. Do you like maths?
Maths.
Can you come down here for a second? I want to show you something. I think maths is all marketed wrong. I think there are really three levels. The first one is calculating, which is just rechnen, you know, you have to grind your way through that level. Nobody likes times tables. The level 2 is actually applied maths, doing something useful with it. You know, like in your last exams when you were calculating how many toroidal donuts you would get with that much dough and this kind of stuff. And then the level 3 is actually proofs. I want to tell you a story about little Charlie Fred. So he's in primary school and his school teacher could not be bothered to do a lesson. So he just said to all the kids, just add up all the numbers from 1 to 100. The first one who's finished can just go home. So he wants them to do 1 plus 2 plus 3 plus 4, all the way plus 100, right? This is grinding, calculating as much as you're ever going to get. The kids start adding 1 plus 2 is 3 plus 3 is 6 plus 4 is 10 and so on and so on. But little Charlie Fred, he writes 5,050 on his paper, gives it to the teacher and goes home. So how did he do that? What Charlie Fred did was he grouped the numbers together, of course. So he said 1 plus 99, that's 100, right? 2 plus 98, that's also 100. And 3 plus 97, that's 100. And so on, until 49 plus 51, that's 100. And at the beginning, you can also say 0 plus 100. That's also 100. Because of course we can just add for the number in front, we can just add a 0. So 50, of course, you can't say 50 plus 50 because there's only one 50. So 50 is sort of special at the end. How many of these numbers do we have here? Does anyone know?
50.
50, exactly. So it's 50 numbers and a 50. So 50 times 100 is 5,000 and plus another 50 is 5,050. So that's how Ghost got there. So that's a cool trick, but maths is all about generalization. So instead of just going up to 100, how about n? We want to have 1 plus 2 plus 3 plus all up to some number n. How would we work this out? If you draw this out on squares, you have sort of 1 plus 2 plus 3, right? 1 plus 2 plus 3 plus 4. How many little boxes are there here? How many is that supposed to be? N. N, that's correct. N. But then if we move this thing to up here, we get a rectangle, right? So this is n wide. And how high is this rectangle?
N plus 1.
N plus 1. That's right. So our theory here is that if we add up all these numbers together, that it is n times n plus 1, but we only want half of it, right? So we think this is a half n times n plus 1. So let's try a couple of numbers. So 1 is a half of 1 times 2. What's 1 times 2? 2. So it's 1. So that's correct. 2 is 2 times 3 is what? 6. And half of that is 3. Yeah, that works. And well, let's put in 100, the Charlie Fred's number. So 100 times 101 divided by 2. What's this? So 100 times 101 is 10,100. Divided by 2 is
5,050.
Ta-da!
Level up.
Did Charlie Fred exist or did you just make him up?
Yeah, he existed. He's actually called Carl Friedrich Gauss. And he did many extraordinary things and one normal thing for which they put him onto a 10-mark banknote.
Normal thing?
A maths joke, never mind. How do we prove that this is actually always the case? And there is a really nice way of proving this. It's called an inductive proof. So we're going to test the first number out by hand and make sure that that works, which we've done. You know, if you put in 1, you get out a 1, so 1 is good, right? And then we work out, well, assuming that the n-1 case is correct, we prove that the n case is also correct. And that means, you know, if it works for 1, then it'll work for 2, and then if it works for 2, then of course it works for 3, and if it works for 3, and so on and so on and so on. Inductive proof, very nicely, very nice. Okay, so the case of 0 plus 1 plus 2 plus to n-1, we assume we know that is a half, and then n-1 times n-1 plus 1, which is just n. So we assume that that is correct. So the 0 plus 1 plus 2 plus plus n-1 plus n is that a half n-1 times n plus n. And now we have to do some maths with that. And I think it would be a good idea if you had a go at this. So here's some pens. Okay, go for it.
So first we need to turn it into a fraction. So we have n squared minus n divided by 2 plus n. And this, we need to put it to the same denominator. That's n squared minus n divided by 2 plus 2n divided by 2. And we can simplify it to n squared minus n plus 2n divided by 2. And this, we can simplify it even more to n squared plus n divided by 2, which then equals n times n plus 1 divided by 2, and this is our formula.
Great. So I think now we can write QED underneath.
Level up.
Look at where we're standing. If we zoom out from this rock here, you can see the whole planet. If you keep zooming, eventually you see the solar system. And if you zoom a long way, you finally find other stars, and then more stars, and then the arms of our galaxy until you finally see the whole galaxy. But if you keep zooming out further, you see more and more galaxies, all with hundreds of millions of stars. And in all of them, the laws of physics hold. So that we assume that even in the furthest other galaxies, there are electrons and atoms the same way as there are here. But you can also imagine other universes that might exist with different planets or no planets or completely different concepts of space and time, all of them completely alien to us. And in all of them, this formula that you've just proved actually holds. Maths is the closest you get to absolute truth, and that's why I like it.
Who wants to play football?
I'm going to go.
This video channel concerns itself with some original ideas about fundamental physics, but there are some maths gems interspersed. Look for the green thumbnails. I've been following 3 Blue 1 Brown's Summer of Maths since its inception, and this year I really wanted to participate, so this is a video with a very different feel than usual. I hope you liked it. Thanks for watching.